Hello, everyone. Today, I'm going to present Concordia. It's a library for generative agent-based modeling. It is open source, and you can find it on GitHub. The link is here. This is a joint tutorial with, my name is Sasha. I'm a research scientist at DeepMind. This is a joint tutorial with people from SAFE, which is Cooperative AI Foundation. So today I will talk about the library, kind of explain what it is for, how it's generally structured, and how you can start playing and working with it. But just before I dive in, I want to mention a few words about our motivation. We are a group of scientists that are interested in modeling emergent social behavior and social phenomena, and the way we go about it is agent-based modeling, where we take model of individual decision-making, some sort of model of environment, put it together like into an alchemy pot, and look for emergent behaviors. The way we structure this library is, you can think about it as a generative, like simulation in this library is like sampling from a generative model of social interactions in language. The simulation is structured similar to a role-playing tabletop game like Dungeons and Dragons, where there are several actors that play different roles and generate behavior, and they generate actions and consume observations, while there's a game master, which is also in some sense a generative actor, but it has a special role. It controls the context of interaction, the grounding, the rules of the world, and it consumes actions, translates them in some sort of events internally, and then it generates observations that are then consumed by the actors. So who's this library for? Although we're interested in specific things, like modeling social phenomena, this library has broader applications, we think. We sort of cluster them into three main camps that we think this library could be useful to. One is evaluationists. This is something that is dear to our heart as people coming from machine learning community. This looks at the simulation as a multi-actor system where we can assess and compare different agents. So, for example, we could try to see which one of them is best at playing a certain game, or how good are they at solving cooperative tasks, where there's a particular score at the end, or when we were to design a fair evaluation system. Another kind of user that we're envisioning is a dramatist. Is someone who wants to use this library to generate dramatic narratives. You can think about it as an interactive video computer game. And the third type are simulationists, and this is also something that is dear to our heart, because this directly deals with generating social phenomena. Is where we want a realistic pocket universe with little fudging in our pocket, so that we can run simulation of how things could be, or details on how things are. And we are going to try to accommodate all three. So how are we going to model behavior? And we're going to be doing that with predictive pattern completion, and modeling the world as a stage, and all of us are actors on it. So in some sense, we're going to model Adele's behavior as if she's an actor playing the role of Alice, taking all the context that it knows about Alice and producing the actions of Alice. So we will do it with the help of large language models, which are conditional probability distributions over text, or potentially over images and other modalities. And our conjecture is that actually to build the simulation based on this actor metaphor, all you need is an LLM, or pattern completion is all you need. So let's say that there's an internal state Z of the agent, of the actor. It might be the description of who they are, what do they want, maybe their plans and goals, or anything that you might want to put into it, and we'll talk about details how to do that. We're going to generate actions given that state, and then we'll once we receive observations, we're going to update the internal state. And here, both of these both sampling in action and sampling the new state is by using a large language model. So this is all that is required to generate the simulation. So you can implement different decision logics using this library, and here are the two examples, but there could be more. The more sort of classic way of modeling human behavior is the logic of consequences, or rational logic, where the actor considers what kind of alternatives do they have, what are the consequences of these alternatives, assigns some sort of value or desirability to these alternatives, and then picks the one with the highest expected value. You can think about it as a model of a rational decision maker, but you don't have to follow that logic with this type of modeling approach. Although you could just ask these questions to a large language model conditioned on the memories of the agent. But you can also use different logic of what, for example, could be logic of appropriateness, and we take that as an example from the Samuel Mark and Olson paper. And they posit that you could model human behavior as if humans are asking and answering themselves three questions. What kind of person am I? What kind of situation is this? What should a person like me do in a situation like this? And do it. There could be other logics that you could implement. For example, if you're a dramatist, maybe one of the questions would be, what's the most comical or dramatical thing to do right now? Or there might be some logic that includes emotions, or maybe there could be even a model of physiological state of the agent, right? But better than to talk is to show you a little demo. So let's switch now to an example from the library. So what I'm going to do now, so here you can see our GitHub page. So I'm going into the examples. I'm going to pull up the Alice column. And all you need to do to open it is just to click this. I actually already opened it and ran it so that we don't have to waste time on waiting for it to compute and install everything. All I have to do is to put my API key over here and select the model. Don't worry, that API key is no longer active. So I will obviously explain all the details later, but just pay attention. Just notice here, there's a small description, which is a config of the simulation. We'll have two entities, two actors. We have Alice, and we will have White Rabbit. The White Rabbit will have a goal, which is to get to the queen. And we'll have a generic game master. So game master, and it sort of says what it is on the tin. It's generic, tries to maintain a reasonably coherent world where actors can do pretty much whatever they want with some sort of consistency there. And we're going to add a little premise, which is simply the beginning of the Alice story. Then we will create a simulation by giving it the config, the model that we defined above, and a text embedder. It is also defined above. It is used for associative memories in the RAG. Then I ran the simulation for 2 steps. And the output, this is in HTML, which sort of contains all the steps of the simulation. It's just for 2 steps for brevity. So what do we see in every step? In every step, the entity tried, it was first Alice, then the second entity was White Rabbit. They took turns. Alice generated some action, and she took a deep breath and steadied her nerves and began following White Rabbit down the narrow path. We can see how the decision making logic of Alice unfolded. Here we have different components. This is, for example, she follows this logic of appropriateness. What kind of person am I? What kind of situation I'm in? So this is how the answer to what kind of person is Alice was generated. This is the situation perception that was generated for Alice, and then it all comes together in the action component to form the final prompt, which decides what is Alice going to do. And the game master takes that and decides what happens as the result of her actions. I'm not going to go into details, but there's a logical thinking that Game Master went through. Now we can actually play around with this situation a little bit. So let's see where the simulation stopped. Okay, so we have White Rabbit being kind of cautious about Alice, so we can make things a little bit more interesting. I'm going to add to the memory of the Game Master an observation that White Rabbit, as if by magic, finds his feet bound by a ball and chain. There's a keys 2 meters away, and we just add that to the Game Master and run simulation for 2 more steps. So these are 2 steps up from the previous step, but here we can see that the Game Master internalized this event and has communicated that to the White Rabbit, and we can see that White Rabbit in the end is calling out to Alice, asking, please come closer and get the key to free me. So we intervened in this simulation, we added a new object, the Game Master communicated to all the players, and now the players are acting as if that happened. And if we keep the station running longer, the simulation running longer, we will probably see them either Alice freeing up the rabbit, or maybe them having a conversation about it. Okay, so this is just to give you a general view of how the simulation looks like. So the main, let's now go to the main structure of the library and how these things are implemented and how you could interact with that software. So the main concepts, 3 concepts that underpin the library are entity, component, and engine. Game masters and actors are entities. They're made out of components, and the engine is something that takes these entities and puts them into interaction. So I will talk about the engine first, because that's sort of defines the whole structure of the simulation. So what the simulation that you have just seen roughly unfolded through this sequence of interactions. So the engine first asks for all the observations for both Alice and White Rabbit to the Game Master by saying, what does Alice observe? And the Game Master said, Alice sees White Rabbit checking his watch. And the engine took that observation, passed it to Alice. Then he asked what the White Rabbit observes. The Game Master asks provides an observation for the White Rabbit. Then passes on to the White Rabbit. Then engine asks whose turn is next to the Game Master. Game Master says Alice. And then engine asks, what does the Alice do? Alice follows the White Rabbit, and so on. So that's how the simulation runs. And Alice follows the White Rabbit. So these 3 are entities, Game Master, Alice, and White Rabbit, and all that they do is they implement observe and act. So you could actually put almost anything you want. If it implements observe and act, that would work in the simulation. And the engine is what orchestrates the simulation by passing observations and actions between entities. So the engine sort of defines a sequence or simultaneity of high-level questions to the Game Master and the actors. It controls the flow by asking simple and straightforward questions like, what does Alice do next, or whose turn is next? And only assumes that entities implement observe and act. It does not have an LLM inside of it. If it ever needs any sort of natural language logic, it always goes and asks Game Master, or in some cases the actor, if it is about the actor. It can be turn-based or simultaneous, and that would sort of make a difference. So we have several, if you would look in the Concordia environment engines, you will find several engines there, which have different patterns of interaction. So what you've seen already is sequential, turn-based, like a tabletop role-playing game. So that's what you saw here. Alice takes a turn, then Rabbit takes a turn, and so on. They're simultaneous, and you can think about it like rock, paper, scissors. We go 1, 2, 3, and at the same time, we show what our action is. This is slightly more scalable, but obviously requires more sophisticated game master to resolve, but appropriate for some type of games and simulations. And then there's parallel, is where actors perform multiple actions in parallel to each other and themselves. That sounds a little bit grand, but what it is meant to say is it is a bit like survey or a poll, where we have a particular actor and you give it loads and loads of questions, all are being answered in parallel and not being remembered by the actor. And you can also do it in parallel to many on many actors. So this is to implement surveys and polls. You can see in we might actually have time to look at an example today. So obviously that is the parallel one is very scalable, but is a kind of lower fidelity. There's less interactions possible between users. Yes, please help. Please, Chandler.
Are there any limits on the number of agents that can be in a scenario?
Computationally, yes. But in theory, no. So the more actors you have, the harder it will be to scale. So sequential, if it's a sequential, then it will be the same situation as playing a turn-based game with a really large group of people. You spend most of the time waiting for your turn. If it is, say, parallel, then it is a lot more scalable because everything's happening in parallel, but also the amount of, although the time will go faster, the amount of queries you're making to the LLM will be high. But the library doesn't put any explicit limits on the number of actors, but the limits arise through your computational constraints. Okay, so thank you for your question, Chandler. Now let's look at the entities and components, what makes both actors and the game masters. So the main key idea here is that instead of writing one big prompt to model a particular type of person or an actor or a game master, we'll be using modular, flexible components that are reusable and interchangeable. So the picture and the design pattern is that the world consists of entities. So there are game master entities, there are actor entities, there could be actor, even maybe a central bank could be an actor in a simulation, which is a non-human, non-person entity. They have simple interfaces, is act and observe. And they're simply containers of components. On their own, entities do not actually implement any logic that is behind their behavior. Everything that makes an entity unique is injected by adding components. And components are actually what implements functionality like LLM calls, retrieval augmented generation, reasoning, personality traits, you name it, everything. And the same as with the game master. So again, as I said, actors and game masters are all entities. And what makes a difference is the components that they have. So both game masters and actors would most likely have memory and observation components that arrange all the memories and somehow process observations. But actors were more likely to have components that represent identity or situation or the person itself or their psychological state or a plan. But the game master will have things like, where is everyone? What's the state of the world? What are the rules of the world? And so on and so forth. And it's components that make a difference. So we will now talk about the actors and get back to game master in a minute. So this is true for both game masters and actors, but entity again is a husk, is an empty shell. And what animates it are components. Most entities will have something like that as a set of their components. Action component is not negotiable. Everyone has to have an action component and only single one, because only one action stream is supported. It's not defined what it means to output multiple actions at once. So there's only one action component. Most of the actors will have memory component, but this is in some sense optional. And then there'll be other components implementing different functionalities. These components can talk to each other. There's an easy way to do it. So when the observation, as I said, the entity receives observations, output actions. So what happens when observations come in? Whenever an observation is coming in, it will be broadcast by the entity to all of its components. And when to elicit an action spec or action specification will come in. All the components, it will be broadcasted to all the components. They will generate context of action for the action component, which will sort of form the header of the prompt to elicit the action. It will get into the LLM, and the action is going to be sampled. Let's zoom in and every component can have an LLM. So let's zoom in a little bit on what happens when the action is being broadcast, or when the action spec comes in to elicit an action. What happens is a sequence of calls. Pre-observe, which is will have an argument of observation. Post-observe, and update. And in case of action, it will be pre-act, post-act, and update. So components implement functionality by latching onto these calls and implementing what to do. So, yeah. So, for example, this is sorry. So this is how the prompt will to action will look in the sort of the space of text. If we drop the blocks and just look at what is the final prompt that generates action, it will usually have some states of components. Here's a component that just summarizes just shows the last observation. There's a component that asks what kind of person is Alice, what's happening, what should she do right now, and so on. These are all the outputs of components that went into the pre-act context of the action component, and then the action component generates the action. Alice will follow the white rabbit. So I already mentioned action specification. This is the like a unit of data that you communicate to the agent when you call act, which just simply tells it what kind of output you should expect, you should produce. So it can be free, simply like just generate text that follows extra specs, for example, like what would Alice do next? And the output can be anything. Or it could be multiple choice, like would Alice follow white rabbit? Yes, no. It could be continuation. It sort of continue the string like Alice would, and then you expect it to continue. It could be a floating point, and so on. So this is the multiple choices are particularly helpful to provide strict grounding for decisions. So, for example, if you're implementing something like voting, then multiple choice questions are great, because then the game master can know for sure what the actor is voting for. And open source large language models have, or open weights, large language models have often have logit output that allows direct max or sampling from a softmax. So again, this is a zoomed-in version. What happens when the act is called in the entity given the action spec? As I said, there'll be pre-act phase when then we call pre-act on all the components in parallel. Then we assemble the context of action, get the action temp. Then we call post-act on all the components in parallel, and then we can all update on all the components in parallel. So we make sure that these parallel calls are thread safe. That is managed by using phases. When observation happens, similar thing goes on. There's pre-observe, post-observe, and update. So the components are made to do what they need to do by implementing pre, post, act, or observe or update functions, using and deriving logic from them. So what kind of components would you write for actors? Well, it depends what kind of actors do you want to simulate, but usually there will be some basic components that everybody needs, like observation and memory. There'll be something about, there could be agentic components that sort of just try to generate some sort of good policy for the agent to follow, like plan or goal or optional, like what kind of options do I have? Could be psychological ones, emotional and mental states. Could be something social, like identity, status, and theory of mind. This is the kind of things that you could try to implement using the components. And then once you have your components, you put them together into an agent. The code usually would look something like that, where you define several components. This is how the components that ask these three questions are defined. And then you put them into a structure that goes into constructing an agent. Yes, Logan, please.
Yeah, can you explain how you implement an agent that plans? You're talking about hierarchical planning.
Mm-hmm. Yeah, sure. So we can look at the plan component. So if we go into Concordia, components, agent, and let's look at the plan. Is that more or less visible, or should I zoom in a little bit?
Looks good.
So the plan component would implement the pre-act, and it will look for a goal. If it component, and if it doesn't, that's fine. It will. It is usually conditioned on other components that it could look for the context of its planning. So it could be goal, but if not, it could be just the recent memories or some sort of description of the agent. Then it will do the following prompting by saying, well, here's my current plan. Maybe this is empty. Then there'll be some sort of prompt that explains what kind of planning are we and what kind of goals are we expecting to find. There'll be some, so we have to define, for example, maybe there's a time horizon, so on. But then eventually what we do is we ask, given the current situation, should we replan or not? And if we should replan, then we ask, well, okay, what's the step-by-step for the agent to achieve their goal, given the mentioned time horizon?
Very cool.
Okay, let's switch back. Thanks you for the question. So, oh yeah, maybe actually while we're here, we can also take a look. So take a look at the how that all comes together into the actor. So, for example, this is the agent that is using the plan. It's a prefab. I will mention them a little bit later. What exactly do they do? But this is where we're building the code that builds different components of the agent. These are the instructions, observation, situation perception, self-perception, personalized situation, relevant memories, goal, and here's the plan. So the plan will depend on the model, obviously, because it needs to do LLM inference. It will depend on other components like perception of the self and perception of the situation and the observation. We'll have the goal and a particular time horizon that we get from the config. And then it will go into the structure components of the agent, plan, and that components of the agent will go into the constructor. Will go into the constructor of the entity agent with logging, and that's how an agent will be made out of this with these components.
Cool.
Okay, very timely question. Thank you. So what you just saw was a prefab. It's a factory that produces configured entities given short config. So this was basic with plan, just what you've seen. Just basic is just the 3 questions. There's a subminimal, which is very close to just a naked LLM, and scripted that's good to execute, which you can give a script to play along with. And when you're constructing a simulation, and that's what we saw with the Alice Collab earlier, you just say, okay, I want this basic prefab of the entity, and here are the parameters, and the prefab will create the entity, and you can just throw it into the simulation. Just to quickly mention, logging and metrics are implemented within the components. Every component can just simply log by calling this function, which is one of its members, logging channel with a dictionary, and it will immediately go into the logs, and you will later be able to see it in the generated HTML that we were looking at previously. Okay, let's look at another collab. Why not? So this is the agent development collab. Again, I sort of wound it a little bit. It's the one I preloaded before. So in this this collab, the simulation is taking place in Scotland. It's St Andrews in 1546, and we generate some procedure to generate some sort of circumstances for agents to interact with. What is interesting is we about this call-up is that we made our own prefab, a factory that creates entities, actor entities. And rather than that being a basic agent, we created this component called the principal, which is a question of recent memories components. It just loads previous memories and asks a particular question to them and outputs that into its state. So rather than being guided by who am I, it will be guided by this. And it will, by this, will be sort of its main guiding principle. And it, in this particular context, in this call, is how can the agent exploit the situation for personal gratification? And when we run it, we can then, so this is the configuration of the simulation, and there's some generated HTML. So when we run it, we can see that the entity that where is it? It's which? Sorry, I just want to see which entity was. So some entities are basic. Oh yeah, this entity was my agent. It will be the other one. So this will be Andrew Douglas, and it's we can now see that when it was producing an action, it in one of his components was exactly the main guiding principle. Andrew Douglas understands James McGregor's desire to involve the university town, yada yada yada. Basically, we sort of we can also look how this was generated. It was generated by asking this particular question to the memories of McGregor, of Andrew Douglas. So you can use this collab by trying to implement different type of principles or play around with this kind of components and see how they change the agent's behavior. So this is a good collab to start to play with the architectures, and you can see how you can easily build an agent out of components. Okay, now let's switch gears and talk about game masters. So again, we're using the metaphor of the stage and the performance on the stage. And in this case, we're going to be talking about the stage itself. So this is slightly an extended picture of how the library works. You can see that there are now multiple game masters here, because this is actually totally okay with the system. You can have more than one game master, and we will see why it's useful later on. So the way to think about implementing game masters is you are pruning the tree of possible futures. So as the actors interact and produce behavior, certain things in the world could be possible and certain things could be not. You can think of, for example, laws of physics prevent certain things. Maybe there is magic in the world you're simulating, but it also has certain rules. So when you're implementing the game master, you're sort of implementing the logic of what is possible and impossible in the world and how to interpret the actions of the agent. For example, you can say, well, there is no magic, and you chopped off one of the branches of the possible futures. Again, it's components that make a difference between the actor and the game master and between different game masters. So what kind of components would you be implementing to make the game master, and what kind of components will you be implementing? So here I plotted the different components of the game master over the axis of the more unconstrained simulation. So think we are doing very little pruning of the possibility trees, and to the extreme of the fully constrained, when the simulation reality is very constrained and very structured. So on the left here, you will have something like a naked LLM. Basically, I know you just stack the observations and give them to the game master, and then the game master is a naked LLM that just answers these questions to the best of its ability. So everything can happen. Maybe magic can happen. The simulation can go wild. Kind of going further to the right, okay, maybe we want to have some sort of consistent rules of the world. Maybe we want to make some nicely moving narrative and push things forward so the agents don't get stuck. Going even further, maybe we can implement sort of a monetary system or markets, or going to very constrained things. It could be a physics engine or an electricity grid, something that has this rigid mechanics, which are modeled maybe even without any large language models, simply in Python or even calling C functions and whatnot. So it really depends what kind of simulation you're building. Will define what kind of components the game masters will have. So what is particularly interesting to our group and to the simulation of the social phenomena is where the interdependence of the agents is mediated through the shared resources. For example, the agents are using the same river, or they have food stock that they manage together. Maybe it could be their calendars, or property structures work the same way. So, and then obviously you would have a component that implements that resource, and it will probably track its usage, simulate the resource lifecycle, manage access, who can use it and who cannot, and when, and so on. So the game master architecture is in many ways defined by the way the engine interacts with it. So we know so this is, for example, the sequential agent, and it has a particular call sequence that it implements. Now, as game master, every time this is a sketch, but it roughly follows the actual engine. Like, well, shall I terminate? No. Okay, let's go on. So which is the game master that will handle this turn? If there's the name of the game master is different from the one right now, let's switch. Then what does each entity observe? Call observer, and then the engine will call observer in this entity. Who's next to act? What's their action spec? And then resolve the action. So, the game master has to be ready with its components to answer those kind of questions. I will do it for components. So there will be usually what it makes it really quite easy is to implement a component that will handle this type of question. So these are the components of the generic game master. It usually handles the next action, who's going to be next, or how to resolve the events, what are the relevant information about the players, and the action component. We use a different action component here in the game master from the actors, because here what it usually does, it looks up if any of the components are suggesting the answer to the specific action spec, and if yes, it uses the state of the component, and otherwise it tries to just use LLM to answer that. It provides more modularity. So, for example, the component tries to figure out who's acting next. Could look something like that. It implements pre-act, gets the action spec, and if the action spec is next acting, its type is next acting. So then it will ask, okay, so whose turn is next, and give it the choice of all the player names, and then they will return the player name selected by the language model, contextualized by the state of components that the next component depends on. So there, as with the actors, Logan, please.
Hey, yeah, I'm wondering if you could also give an example of what the game master would do when called on pre-observe and post-observe.
Well, the game master called pre-observe or post-observe will simply call pre-observe and post-observe on all of its components. So I wonder, is there a specific component you were thinking about, or?
Yeah, I'm just wondering if you had any examples of when that might be useful, or a component to handle something in pre-observe or post-observe.
Yeah, the pre-observe, for example, will be it takes the observation, and the event resolution component will be used for that. So what kind of things does game master observe? It observes actions of the players. So does the game master need to do when it observes the action of the players? It needs to figure out what will be the event resolution, what will be the resolution of that event. So the pre-act will usually take that and perform some logic with it. Probably store in the memory is like, well, this was the action attempt of the agent. So also both actors and game masters they have a component that manages observations, and these are the components that always implement pre-observe. And they take the observation, they would say put it into memory, maybe make some analysis of it, and yeah.
Yeah, makes sense.
Okay, so as with the actors, there's a bunch of prefabs that we already made, and they there's the generic, what it says on the tin. The situated is a generic game master that also takes into account, kind of tracks more precisely the location, the state of the world. There's dialogic, which simulates the conversations. It's a lot faster because it doesn't need to really resolve much of the events. It just needs to pass the utterances between the agents. There's also prefabs to have a more scripted interactions that are useful for games, and I will mention a little bit later as well. So let's just briefly talk about multiple game masters and why this is useful, because you will see it in some of the columns. The reason, the way you can think about multiple game master is having like multiple different game screens. For example, in a action video, role-playing video game like Fallout, you would have different screens for dialogues, combat, and map navigation. Different game masters are doing something similar. It's like having different screens of game rules within a game. So, for example, when the game master, there's a generic one which manages everyone's actions, but maybe when it detects that there's a dialogue happening or a conversation, so it's a dialogic game master that is more efficient at that. Or maybe there's a special game master to measure traveling between locations and so on. You can think about it as also as a simulation within a simulation. And the way we switch between the game masters is just by simply asking the current game master, should there be a switch? There are also special game masters called initializers. Basically, we sometimes would want to generate some sort of initial memories for the agent, right? You don't want to like in the simulation with Alice, it was nice that the large language model already knew about Lewis Carroll novels and could immediately infer what kind of behavior needs be. But if we want to simulate some more realistic scenarios, you need to get more texture, what kind of person where is this person from, what's their story. And these are the initialized game masters are ran before everyone else to generate those initial observations. We have one example that, given the context, generates a life story of the agent so far and adds it to their memory by calling observe. All right, so this now let's look at a few more collabs, and that will, once we're done, that will conclude the tutorial. So you've already seen Alice and the actually, that said, if we would look at where the collabs lie on the spectrum of evaluationist, dramatist, simulationist, then if Alice would probably be somewhere here in the dramatist, while the actor development will be a little bit more towards the simulationist, and then there's one we're going to specifically look at is selling cookies is the evaluationist one. So let's I will just give you a taster of a few different collabs so that you roughly have the idea of what kind of things are possible in Concordia without going into too much detail in each one of them, but you can pick it up from there and play with the collabs yourself specifically. So since we already looked at Alice, let's look at selling cookies, which is a collab which has in mind a more of a evaluationist vibe to it. So this is a game played between so the premise is that there are two players. One of them is a cookie salesman, and his name is Bob. He'll be player 2, I think, is Bob. Player 1 is Alice. He wants to sell cookies to Alice. Alice actually doesn't like cookies, but would do anything for a charitable cause. including buying cookies. And the whole simulation is basically a sales pitch of Bob to Alice. But it's a structured simulation that follows a certain script. So we were going to be using dramaturgic game masters. So it will be a dialogic dramaturgic game master that manages the conversation, and then there will be a game theoretic dramaturgic game master that manages the game. And the game itself is, if Alice buys cookies, 1 point to Bob, minus 1 point to Alice. If Alice doesn't buy cookies, minus 1 point to Bob, 1 point to Alice. And yeah, so and once the simulation is run, there will be a certain score that you will see here assigned to Bob and Alice. And you can see here, this is the simulation. This is a conversation that has happened, and in the end, Alice did not buy the cookies. Thus, the negative score for Bob and positive for Alice. Let's look at how this game is sort of defined. You can obviously dive into this code and see all the details, but there, on a very high level, we define the decision scene here, which is, would Alice buy cookies from Bob? That's the main decision she has to make. These are the options, yes or no. Then we define some sort of rules of the conversation and the scene structure. So in the first scene, they talk, and in the second scene, the decision has to be made. And there is a function to translate their decisions into scores, and their scores into observations, and then all of that information, both the scenes that we generated this way, the scoring functions go into the config. Yes, Logan?
What are scenes?
Scenes are structures that specifically guide the game master to present, to sort of structure the interaction. So, for example, one scene can be when they talk, the other scene is decision scene when they have to make decisions. So if you want to know more details, you can play with this Colab and look at the code. For example, we could also modify this if we would want to modify this game. This is a good call to start playing to implement some game theoretic things. For example, like a prisoner's dilemma or something like that. So the way you could also, for example, we could make the game a little bit different. We could say that both Alice and Bob need to make a decision, and that Bob needs to decide whether to sell cookies to Alice, and the Alice is going to decide whether to buy them, and they will only get points if both of them say yes, if both of them say no. So what I'm doing here, I'm changing the score function such that they only get points when they both answer yes. I'm changing the participants in the decision scene to be both Bob and Alice, and changing and adding the premise for them. And now this is how it looks. We just added another action spec for the decision scene for Bob to decide whether he's going to sell cookies, and for Alice to decide whether she would buy them, and changing the scoring function. So that would turn it into something that is closer to something that you could take this over and just try to implement something like a prisoner's dilemma out of this. We can let it run and look at the last collab I wanted to show you folks. And this is a collab that implements the parallel dynamics, which is just serving questionnaires. So this collab implements giving the stress and depression, stress, anxiety questionnaire to the characters from the Lords of the Rings. So we already ran this collab, and we can see different scores for stress, anxiety, and depression of different characters in the Lord of the Rings. Observe how badly poor Frodo is doing on all counts, which is, I guess, unsurprising given his circumstances, but Gollum is doing even worse, which is unsurprising given his circumstances. So just to show how you could play with that, for example, just for the speed of it, we could only leave Frodo in, and then just before the simulation runs, we can add a little observation. So we're going runnable simulation, give me the entities. I know there's only one, so 0, and I call observe. the ring is destroyed, the Sauron is no more. Frodo is a happy hobbit getting old with his family in the Shire. And if we run that, I will take a second, but we will see that we're getting a much happier Frodo at the other side of the simulation. Yeah, so I hope you folks have had a decent overview of what the system is capable of and what you can start doing with it. I think the best way to engage with the library is just by going to the examples, opening those callouts, putting your API keys and playing around. Well, we can see that Frodo Baggins is not anxious, stressed, or depressed at all once the ring is destroyed, and he's happily living back in the Shire. So yeah, I think on this happy note, I will conclude and take more questions if there are any.
Great.
Great presentation.
Yeah, thank you.
All right, Chandler.
Yeah, I have a question. So are there plans to implement this? Is incredibly customizable. Is there any way that sort of an actor or a language model can use outside tools and or spin up other agents to help with their process or navigating whatever scenario that they're in?
Yes. So the whole library, since it takes it operates the bring your own LLM model, doesn't actually depend on the kind of on the tooling. So the way to integrate the tool use, for example, would be simply, again, for the language of components. So, for example, you would implement a component that would do a certain tool call. It could even call a different language model. It could even be a completely different interface. As long as it's the component takes in something as a string and outputs as a string, this is possible. Does that answer your question?
Yeah, I mean, so if I understand that correctly, basically you can build components to do whatever you want, and as long as it takes in a string and puts out a string, it's sort of free reign to go plug in anything, use any sort of web scraper, calculator, secondary language model with its own. That's incredible.
We should be precise in what take in a string and give out a string means also, right? It means implement pre-observe and post-observe, pre-act and post-act, or whichever subset of that you want, all of which take in strings and give out strings. Yeah.
Yes. Yeah. So the string can potentially contain JSONs, web links to search, images that are just represented as bits and so on. As long as you can pass that internally inside the component, then you can do it.
And that is also true for game masters as well.
Yes.
So they could have specific evaluation criteria, different data dictionaries, those kinds of things. So you could potentially hook up a game master to like a SQL database and track things that way.
Yes. Game Master specifically is a great target for adding components that run something even like not related to large language models like physics engine or a market or monetary system that follows strict rules. Yeah.
Thank you.
Yeah, on that note, let's say that I'm a climate scientist and I have a detailed ecological simulation that takes in actions of certain entities, like how much they've taken from a shared resource. I could just take this simulation that works really well in this kind of closed environment and plug that into a component in the game master.
Yes, in principle, this is possible. I think the main thing to figure out in this case is to align sort of how everything ticks, right? So, but yes, it could be just a component of the game master that, and the game master will be then responsible for translating what actors do in sort of in natural language into the effects on the simulation of the climate, and vice versa, translating the current state of the climate simulation into the observations of the actors. and that and then yes, and I think that's what we had in mind, something like that when we're building.
Yeah, very cool.
Awesome.